A piece of matter, then, is a galaxy of such events. Remember that with the flashes? As a schematic psychophysical parallelism, there it is again. After the flashes, we suddenly have this crazy business about psychophysical parallelism. No, sorry, I shouldn't say craziness because Bell was not being crazy. As a schematic psychophysical parallelism, we can suppose that our personal experience is more or less directly of events in particular pieces of matter, our brains, which events are in turn correlated with events in our bodies as a whole, and they in turn with events in the outer world. I don't think I alleviated any mystery there. That's just indicating to you that on more than one occasion, Bell has, here he goes at even greater length about the situation. So what the hell is, you might wonder, what's going on with Bell here? Here he makes a statement about mind. I forgot where is this from? I don't know. As regards mind, consciousness, I am fully convinced that it has a central place in the ultimate nature of reality. But I am very doubtful that contemporary physics has reached so deeply down that that idea will soon be professionally fruitful. For our generation, I think we can more profitably seek Bohr's necessary classical terms, in quotes, in ordinary macroscopic objects, rather than in the mind of the observer. So if we want to explain experience, we shouldn't understand experience in terms of mind or consciousness, conscious events, but in terms of patterns in macroscopic observables, the things we see. Not directly explaining literally the seeing, but what we speak of as seeing, patterns in the world, tables, chairs, pointers. Typicality. Bell had some of the best and most succinct statements about how crucial typicality is for understanding quantum mechanics. And it seems that Bell's thinking on this subject has been sort of, for many people, just sailed under the radar. So I want to give some quotes about Bell on typicality. Then, for instantaneous macroscopic configurations, the pilot wave theory, Bohmian mechanics, gives the same distribution, probability distribution, as the orthodox theory, insofar as the latter is unambiguous. However, this question arises. What is the good of either theory, giving distributions over a hypothetical ensemble of worlds when we have only one world? He goes on. A single configuration of the world will show statistical distributions over its different parts. Suppose, for example, this one world contains an actual ensemble of similar experimental setups. It follows from the theory, and I think he's talking here about Bohmian mechanics. It follows from the theory that the typical world will approximately realize quantum mechanical distributions over such approximately independent components. The role of the hypothetical ensemble is precisely given by psi squared, I should add. The role of the hypothetical ensemble is precisely to permit definition of the word typical. Another Bell. This refers to Everett. Then there is the surprising contention of Everett and DeWitt, to many worlds, that the theory yields its own interpretation. The hard core of this seems to be the assertion that the probability interpretation emerges without being assumed. Insofar as this is true, it is true also in the pilot wave theory. In that theory, our unique world is supposed to evolve in deterministic fashion from some definite initial state. However, to identify which features are details crucially dependent on the initial conditions, like whether the first scattering is up or down in an alpha track, and which features are more general, like the distribution of scattering angles over the track as a whole, it seems necessary to envisage a comparison class. This class we took to be a hypothetical ensemble of initial configurations with distribution psi squared. In the same way, Everett has to attach weights to the different branches of his multiple universe, and in the same way does so in proportion to the norms of the relevant parts of the wave function. Everett and DeWitt seem to regard this choice as inevitable. I am unable to see why, although, of course, it is a perfectly reasonable choice with several nice properties. Okay, end of part one. I think there's time for part two. 20 minutes, plenty of time. Bye, guys. Everybody can leave now. Now, two people here have heard this already, Tim and Vishnia. This is about, I think this is something I gave about 20 years ago at a Bell Memorial Conference, but I think it's appropriate here. And nobody else here could have been there. You were not there. Tim and of course you remember this. Bell on Bohm. I began this with, and I'm just basically going to read. I began with a preamble for an audience of people, of non-scientists, non-physicists, very broad public audience. I guess I can skip all of that because you don't need the background, you don't need the preamble. So I skipped that, and maybe I will read this. Now, Bell wrote much and lectured much about his theorem and its implications. But he wrote and lectured as much, if not more, concerning the virtues of what is the most famous of all hidden variable theories, that of David Bohm. The question thus naturally arises, why did Bell spend so much time and effort expounding upon a theory of just the sort that he himself had shown to be, if not impossible, unworthy of consideration? This was the common view, that Bell had shown that. Indeed, some physicists have spoken of two Bells and have suggested that Bell must have been schizophrenic. I intended not to read that, but because of Federico's talk, I wanted to reiterate this idea of the two Bells. What was the title of Federico's talk? Twin Bells? Twin Bell, yeah. I wish to argue that the Bell twins. I wish to argue that there was, unfortunately for us, but one Bell, and he was the sanest and most rational of men. There is something else that I'd like to do. I would like to convey a small sense of Bell's wonderful style, wit, and clarity. So, to the extent possible, I shall allow Bell to speak for himself. I shall read excerpts from Bell's articles on the foundations of quantum mechanics, which pertain to our question. These articles are all collected in his marvelous book, Speakable and Unspeakable in Quantum Mechanics. Well, I would urge all of you, and indeed anyone with an interest in physics, to read this book and then read it again. I shall also have occasion to read from an interview Bell gave many, many years ago now to the philosopher Rene Weber. Now, the code here is, the blue is Bell. The black is me. When I was a student, I had much difficulty with quantum mechanics. It was comforting to find that even Einstein had had some such difficulties for a long time. Indeed, they had led him to the heretical conclusion that something was missing in the theory. Here's Einstein. I am, in fact, rather firmly convinced that the essentially statistical character of contemporary quantum theory is solely to be ascribed to the fact that this theory operates with an incomplete description of physical systems. That's Einstein. Einstein is expressing here the conviction that the supposedly novel quantum randomness will ultimately turn out to be of the same character as the familiar, normal, down-to-earth randomness exhibited, for example, in the behavior of a roulette wheel or a coin flip. The behavior appears random because there are too many relevant details to keep track of. If the quantum description could be completed by the incorporation of such details, the result would be called a hidden variable theory. However, soon after the advent of quantum theory, any hidden variable account of quantum phenomena was mathematically, quote, proven to be impossible. Bell continues. Einstein did not seem to know that this possibility of peaceful coexistence between quantum statistical predictions and a more complete theoretical description had been disposed of with great rigor by J. von Neumann. I myself did not know of von Neumann's demonstration at first hand, for at that time it was available only in German, which I could not read. However, I knew of it from the beautiful book by Born, Natural Philosophy of Cause and Chance, which was in fact one of the highlights of my physics education. Discussing how things might develop, Born wrote, "I expect that we shall have to sacrifice some current ideas and to use still more abstract methods. However, these are only opinions. A more concrete contribution to this question has been made by J.V. Neumann in his brilliant book, Mathematische Grundlagen der Quantenmechanik. The result is that no concealed parameters can be introduced with the help of which the indeterministic description could be transformed into a deterministic one. Hence, if a future theory should be deterministic, it cannot be a modification of the present one, but must be essentially different. By that he means that presumably it must make different predictions. How this could be possible without sacrificing a whole treasure of well-established results, I leave to the determinists to worry about." Having read this, Bell says, I relegated the question to the back of my mind and got on with more practical things. Bell continues, but in 1952, I saw the impossible done. It was in papers by David Bohm. Bohm showed explicitly how parameters could indeed be introduced into non-relativistic wave mechanics with the help of which the indeterministic description could be transformed into a deterministic one. More importantly, in my opinion, the subjectivity of the orthodox version, the necessary reference to the observer, could be eliminated. Moreover, the essential idea was one that had been advanced already by de Broglie in 1927 in his pilot wave picture. Let me briefly try to indicate the sort of thing Bell had in mind when objecting to the subjectivity of orthodox quantum theory by means of a perhaps extreme example. Concerning the implications of quantum theory, in fact, of Bell's theorem itself, about which more later, a very distinguished physicist once wrote that, quote, "the moon is demonstrably not there when nobody looks." More Bell. Bohm's 1952 papers on quantum mechanics were, for me, a revelation. The elimination of indeterminism was very striking, but more important, it seemed to me, was the elimination of any need for a vague division of the world into system on the one hand and apparatus or observer on the other. I have always felt since that people who have not grasped the ideas of those papers, and unfortunately they remain the majority, are handicapped in any discussion of the meaning of quantum mechanics. Here's from the interview with Rene Weber. In my opinion, the picture which Bohm proposed then completely disposes of all the arguments you will find among the great founding fathers of the subject, that in some way quantum mechanics was a new departure of human thought, which necessitated the introduction of the observer, which necessitated speculation about the role of consciousness, and so on. All those are simply refuted by Bohm's 1952 theory. In that theory, you have a scheme of equations which completely reproduces all the experimental predictions of quantum mechanics, and it simply does not need an observer. So I think that it is somewhat scandalous that this theory is so largely ignored in textbooks and is simply ignored by most physicists. They don't know about it.